Hey everyone, welcome back to my channel. In this video, we'll be solving PYQs of the chapter Newton's Laws of Motion. They will be so in this session we'll take up J mains problems, and in the next videos we'll take up J advanced problems as well. So yeah, you guys also do try these problems with me because otherwise I don't think you can really learn from these problems. And if you do want more sessions like these, please hit the like button and do subscribe. So with that, let's move on to the first problem. So we have a particle that is moving in the xy plane, and it experiences a velocity dependent force where vx and vy are the components of velocity. A is the acceleration of the particle. Then we have to say which of the statements are true. So option A says that v cross A is coming out to be constant. So okay, so first of all, if we write the acceleration vector, so the acceleration in the x direction is going to be k by m, and acceleration in the y direction will be k by m vx. Okay, and ax I can write it as dvx by dt, and ay I can write it as dvy by dt. So now if I divide both of these equations, I get dvx upon dvy, vy upon vx. So from here we get dvx. So if I solve this indefinite integral, I'll get vx squared equals vy squared plus some constant. Now going back to option A, so if I try to find out v cross A, v is going to be vx vy 0, and this acceleration it'll have some constant k. It'll be vy vx and 0. So if I try to solve this, it'll come out to be vx squared. From here we can see that vx squared minus vy squared is some constant, so this turns out to be another constant. So option A is correct. F arises due to a magnetic field is clearly wrong, because if you try to find v dot A, this is clearly non-zero, right? Like it'll be vx vy plus another vx vy. So the dot product is not coming out to be 0, whereas the force that arises due to a magnetic field on a charge is actually perpendicular to the line of motion, right? So this is wrong. The kinetic energy of the particle is constant in time. For the kinetic energy of a particle to be constant, the tangential acceleration must be 0, which means the acceleration must be normal to the velocity vector. But clearly a dot v is not 0, and hence option C is also wrong. And clearly option D is also wrong, because v dot A does not come out to be constant. So moving on to the next problem. In this problem, we have a spaceship that sweeps stationary interplanetary dust, and as a result, its mass increases at a rate given by this. V is the instantaneous velocity, and we have to find the instantaneous acceleration. Let's say this is a spaceship and it is moving with some velocity, v as a function of time, and there are a lot of dust particles here which are stationary. Basically what's happening is that as it moves towards the right, it collects these individual dust particles, and with a rate which is given by this, clearly we can see that the speed of the spaceship is going to go down, right? Because these individual dust particles will apply a force on the spaceship. So because of that, the acceleration will be in this direction. So let's say it's A. Now if we look at an individual dust particle, this sand particle is about to collide with this spaceship. So initially, before the collision, it is at rest, and after the collision, it'll stick to the space. It'll move with the same velocity as the spaceship, which is going to be v. If we observe this sand particle, its velocity went from 0 to v in, let's say, some dt time during the collision, and let's say the dust particle's mass was dm. So the force that was imparted on this is going to be dm multiplied by its acceleration, which is v divided by dt. The opposite of this force, so the force on the dust particle was in this direction, so the force this dust particle applies on the spaceship will be in this direction. Okay, so that force is going to be, now the thing is, dm by dt is given to us, right? Dm by dt is given to us as b v square multiplied by v, so this comes out to be b v cube. This is the force that is imparted on the satellite. So, but as we need the acceleration of the satellite, it'll be the force imparted, which is just bv cube, divided by its instantaneous mass, and its mass as a function of time is going to be m. So the answer will be B option. So we have a small ball that is thrown up with a velocity u. The ball experiences a resistive force of m kv square. We have to find the maximum height attained by the ball. So its resistive force is m kv square. So the acceleration of this ball is going to be kv square plus g. So we have to simply find the max height attained, and at the maximum height, the velocity will be 0, instantaneously 0. So we know the acceleration of the particle is going to be minus kv square plus g. Now, as we need the maximum height, let's express acceleration as v dv upon dy. So now separating the variables. Okay, so now all I have to do is integrate from 0 to h max and the velocity from u to 0. So now how do we integrate this? So if I substitute the denominator as some t, so kv square plus g as some t, then I get, so I'm going to multiply the numerator with 2k. So the denominator is going to be 2k. So now it's simply going to be dt upon t, which is just log, right? So this is going to be log of kv square plus g. So the h max comes out to be 1 upon 2k ln of ku square plus g upon g. And that comes out to be option D. So moving on to the next problem. So we have a ball that is thrown vertically up from the ground. So we have to talk about the correct momentum height curve. So momentum is simply the mass of the particle multiplied by its velocity. So essentially we just have to find the velocity's variation. So initially the velocity is in the positive direction. The positive direction is taken as the upward direction, by the way, and it's moving towards h max, right? So h max is this point. This curve shows that initially it started from this point with maximum momentum, and the arrow's direction is wrong, as you can see. So this is wrong. And here also the arrow's direction is wrong. It should go from maximum momentum to maximum height, right? So even this is wrong. So it's either option C or option D. Now, and in between option C and option D, one curve is linear and the other is varying as something else. So let's see. So using kinematics 1D formula, let's say this height is h. So we can write the velocity at h to be u squared minus 2gh. Now clearly you can see the velocity is varying with height as a parabolic function. So option D would be the right answer. So we have a body that is moving under a constant force, and its velocity, its initial velocity is this, and its velocity at time t equal to 10 seconds is given to be this. We have to find the force. So as the body is moving with constant velocity, so the rate of change of velocity is defined as the acceleration. I can write dv equals adt. Now as the acceleration is constant, we can take it out of the integral, and at time t equal to 0, the initial velocity was 6i minus 2j, and at time t equal to 10 seconds, the velocity vector was 6i cap minus 6j cap. So from here we'll get 10 times the a vector equals 8j minus 6i cap. So from here the acceleration vector comes out to be minus 3 by 5 I cap plus 4 by 5 j cap. Okay, so as they have asked the force, the force is simply mass times acceleration. So this comes out to be minus 3i plus 4j, and that would be option A. So there's a printing mistake here. This would be I cap. Option A would be the right answer. Moving on to the next problem. So in an elevator, it's given that an elevator in a building can carry up to a maximum of 10 people, with the average mass of each person being 68 kgs. The mass of the elevator itself is 920 kg and it moves with a constant speed of 3 meters per second. The frictional force opposing the motion is 6,000 Newton. If the elevator is moving at the full capacity, the power delivered by the motor to the elevator must be at least. It's given that at maximum capacity, it can carry 10 people with an average mass of each person being 68 kilos. So the total mass of that the elevator can carry would be 10 multiplied by 68. So weight of all of those people combined would be 680 kilos multiplied by g, which would be 6800 Newton. Given that the elevator is moving up, which means the frictional force acting on the elevator must act downwards, and its magnitude will be 6000 Newton. And it's also given that the mass of the elevator is 920 kilos. So the weight of the elevator is going to be 920 times g, which is 9200 Newtons. So the net downward force would be 22,000 Newton. Okay. So if we want to take this elevator upwards at a constant speed, the force by the rope pulling the elevator must be 22,000 Newton. So the power that must be delivered by the rope should be equal to the dot product of force and the velocity. And the force is going to be 2200 multiplied by the velocity of the lift is given to be 3. So the answer would be 66,000 watts. And that would be option D. So moving on to the next problem, we have two blocks of mass M1 and M2 that are connected by a metal rod of mass 8 kgs. The system is pulled upwards vertically by a force of 480 Newton, and we have to find out the tension at the midpoint of the rod. The weight of M1 will be 20 G, that is 200 Newton, and the weight due to the rod will be 8 multiplied by G, that is 80 Newton, and the weight of this mass M2 is going to be 120 Newton. As the mass M1 rod and M2 will move as a system, let's say its acceleration is going to be A. So we can find out A as the net upward force is 480, and the net external downward force is going to be 200 plus 80 plus 120, that is going to be 400, divided by the total mass of the system, that is 40. So this comes out to be 2 meters per second square. Okay, so now as we need the tension at the midpoint, let's draw the FBD of this part of the structure. So the tension acting here, let's say it is T, we have to find T. So the weight of half of the rod is going to be 40 Newton, and the weight of mass M2 is 120 Newton. So, and we clearly know this structure is moving upward with an acceleration of 2 meters per second square. So we can say the net upward force, just T, minus the net downward force, which is 160, equals the mass of this part. So this is 4 kgs and this is 12 kgs. So the mass is going to be 16 kgs times its acceleration, which is 2. So the tension at the midpoint comes out to be 192 newtons. That is option D. So now let's solve a problem from J Advanced. So we have two particles of mass m and that are each tied at the ends of a light string of length 2a. The whole system is kept on a frictionless horizontal surface with the string held tight so that each mass is at a distance a from the center P. Now the midpoint of the string is pulled vertically upwards with a small but constant force F. As a result, the particles move towards each other on the surface. We have to find the magnitude of acceleration when the separation between them is 2x. They are kept on the horizontal, let's say they are kept on the ground, and the string joining them is now pulled upwards. And it's also given that the particles don't leave the ground. So which basically means the normal from the ground. So there will be normal force from the ground, and there will be the weight of this ball mg, and there will be tension force T that will pull the ball along the string. And the magnitude of the force pulling the string is given to be F. So now as this point, let's say P is massless, we can say the net force on this point must be 0. So the tension along the string is going to be T. It's going to be T because of this string as well. Let's say this angle is theta. So by symmetry, we can say even this angle is theta. So balancing the forces on the vertical direction, we can say 2t cos theta equals F. And from here, we can get the value of tension as F divided by 2 cos theta. Now this distance was given to be x, and the length of the string is a. So the height of this triangle is going to be square root of a squared minus x squared. Now it's given that these balls move towards each other and they don't leave this horizontal plane. So which basically means these balls don't have a vertical acceleration. They don't leave this horizontal plane. So the vertical acceleration is 0 and the horizontal acceleration remains, and that will be because of the t sine theta component divided by the mass of the block. So this comes out to be F by 2m tan theta. Which is basically F by 2m x divided by square root of a square minus x square, which is option B. Moving on to the next problem. So there's a string that connects these two masses 2m and m together, and this system is suspended by a massless spring as shown in the figure, and it's given that this string is now cut. So we have to talk about the acceleration of this mass 2m and m instantaneously after cutting this string. We have to keep a key concept in mind while solving these problems, and it is that instantaneously after cutting this string, the extensions that were already present in this spring will remain exactly the same. So let's say if the spring was extended by an amount of x naught, that will still be x naught immediately after this string is cut. So let's say if we cut this string, and now let's draw the mass FBD of mass m. So there is only one force acting on it, and that is mg. So the acceleration of this block is going to be g, right? And now the spring force here, okay, so now let's talk about the mass 2m. So initially, as the block was in equilibrium, so let's say this spring force that was applied on this block is, let's say, F. And let's say the tension here in this string is T. So we can, through balancing the vertical forces on 2m mass, we can say F must be equal to T plus 2mg. And by balancing the vertical forces on this mass m, we can say T equals mg, right? So from here we'll directly get the value of force F to be 3 mg, or you could have just considered both of them as the system. And now F is simply equal to the weight of this because the tension is now internal. Now as we have the spring force to be 3 mg, now let's draw the FBD of mass 2m. As I said earlier, the spring force won't really change instantaneously after the string was cut. So this force is still going to be 3 mg. And the weight of the block is going to be 2 mg. And from this FBD, we can clearly say the acceleration of this block is going to be 3 mg minus 2 mg over 2m, which is going to be g divided by upwards. So the block of mass m will move with will just undergo free fall, and this 2m mass will move upwards with an acceleration of g by 2. So option C is the correct answer. Problem, we have a string of negligible mass which is going over a clamped pulley of mass m, and it supports a block of mass capital M as shown in the figure. We have to find the force on the pulley by the clamp. So clearly the pulley is in equilibrium, so let's try to draw the FBD of it. So this string here, we'll try to pull it with a tension T, and there is this string over here, we'll try to pull it with a tension T. Now the tension is going to be uniform throughout the string because it's massless, and as this pulley has some mass, so its weight will act at the center of mass and its magnitude will be equal to mg. Now as this pulley has to be in equilibrium, let's just say the force that the clamp applies on the pulley is in this direction. Let's say it's F. All these force added up vectorially should result in a zero resultant. Now how do we determine T? So as this mass m is in equilibrium, we can say the tension on top is equal to the weight of the mass mg. So from that we can say the tension T equals capital Mg. So now let's try to draw a vector triangle. So let's draw a point FBD of this pulley. So it will have a tension T, which I'm going to mark as mg, acting in this direction. And this tension T will be mg in this sense. And then there will be weight of the pulley, which will also be along this direction, mg. So now let's say the resultant of these forces is, let's say, in this direction. So the force applied by the clamp must be opposite to this resultant and equal in magnitude so that they both cancel out. So now all we have to find is the resultant of these two. Now as these two are perpendicular vectors, so which will be option, this would be capital Mg. Okay, so the option D is the correct answer. So moving on to the next problem. So we have an insect that is at the bottom of a hemispherical ditch. It crawls up the ditch but starts slipping after it is at a height h from the bottom. If the coefficient of friction between the ground and the insect is 0.75, then the height h is. Okay, so let's say initially the insect was over here, and it's given that after it climbs a height h from the bottom, at this point it starts slipping. So why is it starting to slip at that point? Let's try to understand. So let's try to understand the forces acting on this. So as this is theta, the tangential component of this force is going to be mg sine theta. The insect would not slip if the friction force acting on its body is equal to this mg sine theta. But the moment this friction force is not enough to support this mg sine theta, this insect would start to slip. Now we know this friction force clearly has its limit, right? As clearly this angle theta begins to increase, we know mg sine theta will also begin to increase, and at the instant when f reaches its maximum value, that will be the point at which the insect will start to slip. And we know the maximum value, or you could say the limiting value of friction, is simply mu times the normal reaction at that point. What is the normal reaction on this insect? It will be mg cos theta, right? So the f limiting would be mu mg cos theta. So when this will be equal to, so when the force of gravity, that is mg sine theta in this case, when this becomes greater than the limiting value of friction, which is mu mg cos theta, this is when or we can say when tan theta is greater than mu, this is the condition this insect will start to slip. Okay, so as we need the condition in which it just starts to slip, we can say tan theta equals mu, and mu is given to be 3 by 4. So from this right triangle, we can say this length is going to be r cos theta, and radius is given to be 1 meter. Cos theta will be 4 by 5. So this is 4 by 5 meters. That is 0.8 meters. So this height h will be 1 minus 0.8, that is 0.2 meters, which would be option A. So in this problem, we have two blocks whose masses are 1 kg and 3 kg, and they're kept on a table. The coefficient of friction between A and B is given to be 0.2, and between the surface of B and the table is also 0.2. Is given that the maximum force F that can be applied on B horizontally so that A does not slide over the block B. Okay, so now let's talk about, so when will A start sliding on top of block B? So this block will start to accelerate, and in order to prevent relative motion, friction will act on this block in the rightward sense, and the same force of friction will act on the block B in the backward sense, right? When we start to increase this force beyond a certain limit, the friction below this block is going to reach its limiting value. At some particular value of F, the friction is going to be limiting below the block A. And if we increase this force F by any amount greater than that particular value, then this block A will start to slip on block B. So that is it. So that is the concept of this problem. Now, what is the limiting value of friction? That is pretty easy to find, right? So F limiting would simply be mu times the normal reaction. And the mu between A and B is given to be 0.2. Normal reaction is going to be the weight of this block A, that is 10 newtons. So this comes out to be 2 Newton. So the force acting on block A is 2 Newton. So what will be its acceleration? So its acceleration will be 2 divided by 1, which is 2 meters per second square. Now, as both these blocks are moving together, we can say even block B is moving towards the right with 2 meter per second square acceleration. So one thing we missed is the friction force here. That would simply be equal to mu n, right? Because there is relative motion between the surface of block B and ground. So the friction here will always be kinetic, or you could say limiting. Let's name it FB. So FB is going to be, mu is same only 0.2, but the normal reaction is different. Normal reaction would be the weight of these two blocks together. So that is 40 newtons. So this comes out to be 8 Newton. So this FB is 8 Newton. Take the FBD of block B and write F equals ma equation. We can say F minus 8 minus 2 equals the mass of B times its acceleration, which we found out to be 2. From here, we'll get the value of F as 16 newtons, which would be option B. We have two masses, M1 and M2, whose mass are given, and they're connected by an inextensible string over a frictionless pulley. They're moving as shown in the figure. The coefficient of friction horizontal surface is given to be 0.15. So the friction here is 0.15. The minimum weight M that should be put on top of M2 to stop the motion. Okay, so what this problem is trying to say essentially is, so I want you guys to make sense of the fact that this situation and this situation shown in this figure is exactly the same. So if I take this entire thing to be a system, then there are two external forces acting on it, and one is going to be this M1G and one is going to be this friction over here. So we have to find this maximum value of this mass M. So now try to feel this problem. So as we increase this mass M, the normal reaction from the ground will increase and the limiting value of this force will increase. And if it increases to a point where it will just be equal to M1G, then our job is done. So that is exactly what we'll be doing. So let's do that. So basically when M1G has to be equal to the limiting friction. And the limiting friction, we know it's equal to mu, which is 0.15, times the normal reaction, which is M plus M2. So this will be 100 divided by 3 minus 10. So which comes out to be 23.33 kgs. So the answer from the options will be B option, because that is the minimum amount of weight from the given options that we can put on top of M2 that will stop the motion. So option B will be the answer. So this will be the last problem of the session. If you enjoy the session, please do like. It gives me a lot of motivation to create new videos. So let's go into this problem. We have a particle P that is sliding down a frictionless hemispherical bowl. It passes the point A at t equals 0, and at this instant of time, the horizontal component of its velocity is v. And this bead has the same mass as this, and it is ejected along the horizontal string AB with the speed v. So even this is given the same horizontal speed as particle, and the friction is to be neglected, and is given that the time Tp and Tq required by P and Q to reach point B is given. So we have to make a comparison between the time taken to reach B. And the only information that is given to us is that their horizontal velocities initially is the same. This problem will be solved. You can solve this problem easily if one thing clicks into your head, and that is that its horizontal velocity is exactly the same. There is a reason that they have given that hint. It is for us to think along the lines of the horizontal displacement. So if you see carefully from A to B, if you see carefully, both of the particle have the same horizontal displacement, right? They both have the same horizontal displacement, AB. So if I just draw a VT curve, I mean Vx versus T curve, if I try to draw that, then the particle Q will have a constant velocity of V throughout, right? It will have a constant velocity of V throughout. And let's say this is the time takes, and the time it takes is given to be TQ. But the particle P is kind of different. It starts from this point only, but its horizontal velocity will start to increase, right? Because there is a component of weight that is accelerating the speed, so its speed will increase. So its speed will increase until this bottommost point, and then it will start to decrease. So it will be something like this. It will increase up to this point, and then it will start to decrease. And finally, when it reaches that, its velocity will be v. Now, clearly, by just comparing the areas under this curve, which is actually the displacement, right? So the area under the curve must be the same for both these. So for Q, this is the area under the curve, right? So, and this will be equal to the distance AB. So obviously the time taken by P will be less than the time taken by Q. So by the graph, we can clearly see that the time taken by P is going to be less than the time taken by Q, and hence option A is the correct answer. Hope you enjoyed this session. Do comment down below if you guys would like more of these sessions, and comment down below what chapter would you like to see next. And thanks for watching.